Welcome back. Let us continue with material balances. It's a very useful principle. We're going to show where all we can use that. At least we're going to highlight where all we can use that. This is an introductory course. So this session or this lecture is on material balances, the useful form of that in fluid systems. We all know what a fluid is from high school. Fluid is a substance that takes the shape of the vessel containing it, and examples are liquids, gases, and so on. And fluids are integral to biological systems. The cell, which is the fundamental functional unit of life, is about 70% water, okay, which is a fluid. So there you have it, 70% of something, the fundamental unit of life itself is a fluid. Not just that, life forms, including humans, consist of life relevant fluids such as blood, oxygen, lymph, and so on and so forth, moving to various body parts. We are human beings made up of various cells, various organ systems, and so on and so forth. There are fluids in constant flow in our body, both liquids and gases, which make life possible, human life possible. Okay. Not just that, the bioindustry needs to continuously process fluids as an essential need, as an integral need. Fluids need to move, liquids and gases need to move from one place to another. The bioreaction itself happens usually in a liquid, and then you take out the products of interest and process them to get it of a pure form, concentrated form, and so on and so forth. So all this requires processing fluids in a continuous fashion, usually continuous or batch fashion, that doesn't matter. And therefore, any analysis of biological systems needs to understand the fluid aspects very well. The fluid aspects are very different. You cannot very easily use whatever we know so far directly. They are complex things. Some of those are still not understood properly in our frameworks, and therefore we need to look at fluids. It's probably the first time you're looking at fluids unless you have done a course on fluid mechanics already. It's a very interesting thing to look at, and let us start with material balances in fluid systems. To do this, we will be employing a few derivatives. Okay, you've all done math, you know what, you've all done calculus, you know what derivatives are, the meaning of derivatives, the way to write them, and so on and so forth. There are various kinds of derivatives. There are a few kinds that we use normally. You'd have seen two of these, maybe you haven't seen one of the three as yet, or maybe you have in a physics course or something like that. So let us see what those are. This is a review of the needed derivatives. This is essentially to make sure that all of us are comfortable with the meaning and use of these derivatives. To do this, and not just that, before I get into the actual derivatives, let me repeat one of the aspects, one of the points that I've made already. A mathematical approach makes aspects much more generally applicable, and thus significantly increases our confidence when we use it. That is the reason for converting many things onto a mathematical framework. We can use it with confidence. And one of the common questions, as I had mentioned earlier, is why so much math? Okay, this is the reason for so much math. It gives us so much confidence to blindly apply it. We don't have to worry about, is this really going to be applicable here? Will I get, can I rely on it? Can I use the results that I get here confidently to know what's going on, to design things, to operate things, and so on and so forth? All these questions go away when we use this framework, and that is the reason why a mathematical framework pretty much is used in most of these subjects, and especially this one is highly mathematical. To review these derivatives, let us consider this scenario. We are in a boat, a motorboat, that is equipped with powerful motors as well as with a powerful anchor, a very strong anchor. and we want to measure the fish concentration, let us say in the ocean. And what we have to measure the fish concentration is a sonar device which pings with every fish it encounters and gives you a count. Okay. So, we have a sonar device for fish counts, and we have a motorboat, and the motorboat has strong motors as well as strong engines as well as a strong anchor, which means if the anchor is dropped, it will stay at that place even in the ocean, because ocean has a lot of currents. So, if you don't drop the anchor and if you stop the engines, you can still move with the current. Okay, that's the situation here. Okay, let's do step by step. The fish concentration is a function of the position. These are position coordinates x, y, z, and time. Okay. What do we normally mean by a function is that it can vary, the fish concentration can vary with space, x, y, z coordinates as well as time. If we drop the effective anchors of the motorboat, it's going to stand still at that place and count the fish at that place. The count is going to provide the variation of concentration of fish with respect to time alone, because the position is fixed. Or in other words, the x, y, z coordinates are fixed, and therefore, we are going to have the variation with time alone at that particular point. And that is represented, as you know, by the partial derivative of the concentration of fish with time. We normally say dou t of c. This, as you know, is the way we represent derivatives. It is not the ratio here. It is dou t of c at a constant x, y, z. Okay, that constant c is indicated here as a subscript after the bracket. And many a times, if it is clear enough, we don't even mention this x, y, z. Okay, so partial derivative of c with respect to t at constant x, y, z, and usually x, y, z are not explicitly shown as constants in the partial derivative, except when required to avoid confusion. Next, what we are going to do is, we are going to raise the anchor, start the engines, and move about in the ocean. And while moving about, we are going to count the fish. We are going to use our sonar device and count the fish. In this case, the rate of change of fish concentration will give the, what will it give, we will see when we go through this. If we apply chain rule, you recall chain rule, function of a function, right? So, dc dt, the total derivative of c with respect to t, is the partial with respect of c with respect to t plus the partial of c with respect to x, but x is a function of t. Since we are moving about, the position varies with time. So, dou x dou t plus dou c dou y dou t, this is the chain rule that is coming in here, plus dou c dou z dou t, again the chain rule coming in here. We know that concentration itself is a function of time as well as space, x, y, z coordinates, but x is just a function of time alone. It is space, it is not a function of space. Y is a function of time alone, z is a function of time alone by the same argument. They are only functions of time, x, y, z. And therefore, we don't need to write this as a partial. You know, partial means that it is a function of many variables. In this case, it's a function of only one variable, and therefore, you can replace the partials with the total derivative. If you do that, we get dc dt equals dou c dou t, this is still partial, dou c dou x times, since this is a function of time alone, we have gotten the total derivative here, dx dt, plus dou c dou y dy dt plus dou c dou z dz dt. Now, see this dx dt, dy dt, dz dt are nothing but the components of the boat velocity. And therefore, let me also say this, dou c dou x, dou c dou y, dou c dou z are components of the concentration changes with respect to the boat's position at a certain time. And therefore, the total derivative reflects the concentration changes with respect to both time as well as the observer's position. The respective time is this and the observer's position is this. Okay. And that is what the total derivative gives you. We know what the partial derivative gave at when we drop the anchor at that particular point. The total derivative gives you this. Okay. These two you may already know. So, look at this as some sort of a review. The next one you may or may not know. To understand that, let us say that we shut off the engines, but we are not going to drop the anchor. Okay. If you do not drop the anchor, there are there are currents in the ocean, and the boat is going to move according to the current, right. Therefore, we would move about with the velocity of the current v, which is called the local velocity here. The change in fish concentration with time will depend, of course, on the local velocity. We are moving about, we are at different points in space, the way it is going to change with time and so on and so forth, and therefore, the fish concentration is going to depend on the local velocity v. And such a derivative, which is called the time derivative following the motion, is also called the substantial derivative. Okay. You may have seen this in your physics class, but this is actually what it means. We are moving about and we are counting fish in this case, and therefore, we get it as a function of the motion of the fluid itself as well as time. That is what we represent. The substantial derivative is what is represented as capital D's d dt of c equals dou t of c, which is the partial with respect to t, plus the velocities of the stream have come in the place of the velocities of the boat. Vx dou c dou x plus Vy dou c dou y plus Vz dou c dou z. It is essentially the same as earlier, only thing is that the motion is now dependent on the motion of the current, of the boat with the current. Vx, Vy, Vz are the components of the local velocity, and we can write this more compactly in the vector notation. You are all familiar with vectors from your math course. dc dt equals dou c dou t plus, let me write this and then explain this. Vector v taken a dot product with del of c. What is v? V is nothing but I v1 plus j v2 plus k v3. I is the x component, j is unit vector in the x component x direction, j is the unit vector in the y direction, k is the unit vector in the z direction. v1, v2, v3 are the components in these three respective directions. And del is nothing but I dou x plus j dou y plus k dou z. And if you know that the dot product, this is del of c that we have taken the dot product with the v. When you take the dot product, you do a term by term thing. I dot I is 1 because the angle is 0, cos 0 is 1. I dot j is I j cos 90, and that is 0. I dot k is I k cos 90, that is again 0. And therefore, if you do a term by term thing, what remains are only these aspects, and therefore, this can be represented as v dot del c. Okay. Hope you got this. If you not, why don't you write it, do a term by term thing and see that everything else cancels out except for this. This is the reason why we use a compact notation. Expanding it and writing it every time is rather cumbersome. So, we prefer a compact notation, but a compact notation has this much meaning that goes into it, which I am sure you already recognize. If not, you need to internalize that now. Okay. There is so much processing that is represented by a compact notation. We are going to use these three derivatives extensively in this course. Okay. I think we will stop here for this lecture. We have been at it for some time. It's good to process this first, and then we'll move on to the next lecture. Okay. See you in the next lecture then.